So today I'll be discussing my project, uh, long-term water quality analysis and data-driven conceptual evaluation of the AHIRRS framework for the remediation of the Yamuna River. This research was conducted by me and I was mentored by Dr. Rajesh Khanna Jodhpuri. So to start off, I would go over what I would be covering in my presentation today. So it would begin with a brief introduction and background of the topic, followed by a literature review. Then I'll move forward to the methods and the results. I'll have a discussion over all the findings and I'll close with a final conclusion. Um, so, for starting, the aim of my research project was to assess the spatial and temporal water quality of the Yamuna River. Then, based on this assessment, a data driven algorithmic decision matrix is developed to determine the viability of the various treatment methods. Finally, the project aims to design and propose a decentralized framework, which is called the AHIRRS, or the Automated Hybrid In Situ River Remediation System. The main goal of this project was to address critical gaps in the current river remediation system of the Yamuna River by treating the anthropogenic waste at the drain level by offering physical chemical solution to bridge the loopholes in this current system. Solution bridges existing loopholes in the current infrastructure. Also, by intercepting the industrial waste and domestic waste before it enters the river, this approach will directly protect the health and livelihood of the local communities that heavily rely on the river's water for daily agricultural and domestic needs. The Yamuna River is experiencing severe contamination due to heavy domestic and industrial discharge. This is turning major stretches of the river into open sewer lines. Also, rapid urbanization has completely outpaced current governmental initiatives like the Yamuna Plan, Yamuna Action Plan, and centralized infrastructure such as the STPs. The Delhi NCR Yamuna stretch, which is the location for this research, generates approximately 3491 MLD of sewage every day, with a treatment gap of around 900 MLD per day. Looking at this, we can infer that there is an urgent and critical need for sustainable on-site solutions that can function dynamically without requiring any extensive land acquisition. So as I mentioned earlier as well, the specific area of study which I utilized for this research is a 22 kilometers stretch from Wazirabad to Okhla in the Delhi NCR region. This region was especially chosen because it contains the highest concentration of anthropogenic discharge and untreated drain outfalls along the river course. To effectively capture the long-term data sets and identify pollution trends, I used monthly data spanning from 2013 to 2025. Specifically, the research relies on a dataset comprising of 936 water quality observations collected across seven distinct monitoring stations. The data was collected from the CPCB official website and it focuses on high impact pollution indicators such as chemical oxygen demand COD, biochemical oxygen demand BOD, pH, and water quality index. Next slide. So, coming to the literature review, during the entire course of this project, decades of literature was reviewed and evaluated, and the findings demonstrate that centralized sewage treatment systems such as STPs, effluent treatment plants are frequently overburdened, especially in this region. This is also true during periods of high water levels and monsoon events, which frequently happen in the Delhi NCR region. Recent research also shows that decentralized units largely favors biological treatments such as biofilters. However, a major limitation of these systems is that they are easily destroyed, meaning uh, they are easily destroyed by sudden spikes in industrial chemical toxicity, which can be seen in this region. This project directly addresses the gap which was seen in the literature review by proposing the AHIRRS framework, which is conceptually capable of handling complex waste compositions and highly toxic industrial loads. So to begin with methodology, uh, the methodology begins with rigorous data pre-processing and cleanup. The initial steps of the process involve identifying and removing any statistical anomalies and outlier spikes that were caused by these sensors. Also, to ensure a continuous and reliable data set across the entire timeline, missing spatial and temporal data points were filled up and handled using linear interpolation. Finally, all the indicator units were standardized so that uniform algorithmic processing can take place in the upcoming modeling phases. Once this raw data was cleaned and standardized, the next methodological step was to translate these numbers into ecological profiles. The second methodological step involves dissolved organic matter profiling. This process involved analyzing the critical balance between BOD and COD to determine the water's biodegradability index. After this, the overall water quality index was computed using the standard weighted arithmetic methods. So, these quantitative values of the indicators were then categorized into qualitative boundaries based on the standard environmental guidelines by the Green Tribunal. For example, any COD value which exceeds 50 milligrams per liter was classified as very bad, indicating severe pollution level in the river. Once this raw data was cleaned and standardized, the next step was to once this was done, the next step was to translate these numbers. Deterministic rule-based matrix was developed to evaluate the computed water profiles. This matrix suggested that universally normal water requires no action. Elevated BOD along with normal COD requires a standard biofilter treatment. However, if the water is critically impaired, then the matrix suggested the physicochemical AHIRRS framework. Uh, to verify the precision of these findings, uh, regression modeling was performed, and the regression modeling applied to this data demonstrated extremely high accuracy. It achieved an R squared coefficient of 0.99 alongside minimal error rate, thereby confirming that the evaluations models strict reliability. Because the matrix also identified chemical toxicity that would destroy the standard biological filters, a robust physicochemical framework had to be conceptualized. This led directly to the design of AHIRRS. So, in this slide, the conceptualized AHIRRS framework is discussed. It operates in four different phases to physically and chemically neutralize all of these domestic and industrial pollutants. So, starting with phase one. Phase one is the intake and pre-treatment phase. It operates on a side stream interception principle. So in this, a Jackwell chamber and automated bar screens are utilized to stabilize the hydraulic loading and physically remove any suspended debris, plastics, and other materials which float in the river. This diversion captures the severe baseline pollution exactly at the discharge outlets without disrupting the natural base flow dynamics of the main river. Also, submersible non-cloggy slurry pumps then transport this screened wastewater into the next stage. The next stage, which is phase two, is the core physicochemical treatment. It uses a continuous flow electrocoagulation reactor. Because severe chemical toxicity would destroy these conventional biofilters, this system applies direct current through parallel sacrificial electrodes. This triggers localized electrolytic oxidation and reduction with the theoretical mass yield governed precisely by the Faraday's law. The electrochemical process instantly destabilizes complex organic materials, phosphorus compounds, and colloidal matters through rapid flocculation and charge neutralization. Flocculation, in this sense, means when suspended solids come together and form groups so that they can be removed. After this, an automated polarity reversal mechanism is used so that electrolytic efficiency is maintained and the iron rods are not oxidized or passivization doesn't occur on the electrodes. Moving on to the next phase of this treatment, phase 3 focuses on sludge extraction and dewatering. In this, the coagulated wastewater is released through perforated diffuser manifold placed upstream of a low head check dam. This specific hydraulic mechanism reduces the flow velocity and it promotes passive sedimentation of the flocks which were uh, performed in the last phase, phase 2. Submersible bottom suction pumps are used to extract this deposited sludge with minimal disturbance to the clarified effluent. It also prevents the monsoon driven remobilization of these contaminants. Finally, we move on to phase 4, which is polishing and Bethnic bioremediation. In this, the clarified effluent undergoes nanobubble aeration. It utilizes bubbles, uh, oxygen bubbles preferably, strictly under 200 nanometers in diameter. This size maximizes the surface area to volume ratio and it significantly increases the volumetric mass transfer coefficient to actively replenish the dissolved oxygen levels in the Yamuna River. Also, there's the minute size of these bubbles also leads to deep oxygen penetration speeds uh, of residual BOD and it prevents the release of reduced nutrient species at the sediment water interface. Also, the entire continuous flow operation is optimized in real time by integrating IoT monitoring network. With the complete physicochemical mechanics and engineering architecture of the AHIRS framework, it was then very important to statistically validate the underlying water quality models so that the system's deployment is supported by mathematical proof. To do this, the predictive accuracy of the water quality models was evaluated using multiple linear regression analysis. The regression coefficients confirmed that significant predictors or indicators such as BOD, pH, COD, they strongly correlate with the overall degradation index. Also, residual diagnostics were performed. This verified homoscedasticity, which means constant variation along with a normal distribution. This step was really important because it statistically proves that the algorithmic matrix evaluating the river is mathematically unbiased and entirely reliable across the dataset. So once you've proved the model's statistical reliability, this validated algorithm was then applied directly to the main dataset to reveal the actual water quality stress. So analysis of the 2013 to 2025 dataset revealed consistent and severe water quality stress across all the 936 observations used in the study. The data showed that while BOD level experienced some temporal fluctuation, but the COD levels remained always categorized as very bad, as very bad. Consistently, they exceeded the 50 milligrams per liter house threshold. Also, the water quality index calculation confirmed that this specific 22-kilometer stretch it remains critically polluted all the year round, lacking any capacity for natural ecological recovery, which is common in many rivers in India. And because the river remains highly toxic over the entire study period of 12 years, the decision model gave us a very clear result. The chemical levels were simply too high for the helpful bacteria in the river to survive and work. At this point, it is really common to question why STPs weren't used. And to answer this, while a fully operational STP achieves a higher overall treatment efficiency, it performs about 20% better than the AHIRRS systems. But the STPs have a common limitation. As I established earlier as well, the region faces a massive treatment gap of 900 mld. Building new and massive centralized STPs to cover this 900 mld gap would require a lot of financial investment and huge amounts of land, which is practically impossible in a dense urban area like the Delhi NCR. To be noted that the banks of the Yamuna River are flooded and crowded with slums, highly industrial areas, which makes it impractical to build more STPs. And because building new STPs is unviable and the existing ones are failing under these toxic loads, the algorithmic models rejected them. The model also consistently selected the AHIRRS system. Even when the system operates at 80% of an STP's efficiency, EHIRRS is cost effective and space saving, which made the algorithm prefer this over an STP. It in, intercepts highly toxic water directly at the source of the outfalls. It also reduces the 900 mld daily treatment gap without a massive capital expenditure, which is required for building STPs. After looking at these clear economic and engineering results, it directly led to important insights about the river's overall health and the performance of this model and the framework. Next page. So, evaluating the performance of this mathematical model, the analysis successfully proved that the organic waste and the chemical pollution, specifically BOD and COD, are the main factors driving the river's poor water quality. The data also clearly identified that these exact predictors or indicators showing that massive amounts of organic pollution and severe oxygen depletion in this river are the main causes destroying this specific Delhi NCR stretch of the river. Hmm. It is also very important to note a few limitations in this methodology. To start, the MLR model assumes a linear relationship, which might not perfectly capture the complex natural events which often occur in Delhi, such as heavy monsoon rains, diluting the pollution, temperature changes affecting how fast the waste or the sludge breakdowns, and many other factors. Furthermore, the current water quality calculations focus on organic waste and they do not account for heavy metals or pharmaceutical pollutants. If seen from an environmental perspective, these extreme chemical and waste levels persist even when traditional sewage treatment plants nearby uh, exist. This this ecological reality proves that large centralized infrastructure simply cannot handle the sheer volume of pollution on its own. And this really makes on site treatments absolutely necessary at this point. Moving from these environmental and mathematical findings, the next slide would examine how this data directly supports the specific infrastructure and the management decisions. So, moving to the management decision, the statistical findings mathematically justify the HIRS framework. Also, the data proves that extracting contaminants with electrocoagulation and restoring the depleted oxygen in the river with the help of nano bubbles targets the exact sources of pollution. Also, for proactive water quality control, uh, HIRS operates as a complementary side stream solution modules along the STPs or any pre-existing treatment plants, and it is not meant to operate as an independent unit. Also, to prevent the system from being overwhelmed during the severe monsoons events, it must integrate the automated bypass devices, which many systems involve. Regarding the infrastructure optimization, um, the units require a highly stable power source, whether from the grid, the main city grid, or any renewables, such as solar power. Additionally, the electrocoagulation module relies on a continuous dissolution of sacrificial iron electrodes, which compulses regular maintenance of the system. Finally, for sludge management, because the system converts dissolved pollutants into solid flocks, the recovered waste or the sludge from the river needs to go through strict testing and highly secure disposal. So, to conclude, this 22-kilometer Yamuna stretch remains critically polluted because the conventional treatment systems are continuously overpowered by this toxic industrial loads, and every day 900 mld of untreated waste is entering this river, making it dirtier day by day. This data also demonstrates a clear need for a decentralized physico-chemical treatment. To address this, the AHI-RRS framework offers a scalable and land-efficient solution to intercept and treat the pollution directly at the source. Thank you.